Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basuva Kalyan. So in the 35th session of Graph Theory 2, we are going to discuss a topic called chromatic numbers of familiar graphs. So what is chromatic number? That concept already we know. What is chromatic number? The minimum number of colors required to color a graph. So coloring a graph is nothing but you have to keep a point in your mind, one important idea in your mind, that while coloring, no two adjacent vertices must have same color, or you can say adjacent vertices must be colored with different colors. So that you have to keep in your mind. That is called coloring of a graph. But while coloring of a graph, we have to reduce the number of colors. So once if you reduce the number of colors, so what you can say, the minimum number of colors required to color the graph is nothing but chromatic number of a graph. So today in this session we are going to see what is the chromatic number of some familiar graphs, that is the standard graphs which we know, that is a complete graph KP, cycle with n number of vertices, path with p number of vertices or n number of vertices, a complete bipartite graph say KMN, a wheel WP. So like that, if you consider a tree, for example, if you consider a tree, so those are the standard graphs or familiar graphs. What is the chromatic number of such standard graphs, or you can say familiar graphs? Okay, let us consider the first example directly. Find the chromatic number of a cycle. So cycle, so in a cycle, if you consider a cycle with 3 vertices, it is odd cycle. You can consider a cycle with 4 vertices, it is even cycle. So like that 5, 6, 7, 8. So you have to see the difference, whether every cycle is with the same chromatic number, or is there any difference, that you have to go through. So first start with the C3 and C4, C5, C6, like that. See the difference, whether all these graphs which you have considered are with the same colors which we require to color with minimum number of colors, or the chromatic number of C3, C4, C5, is it the same, or is there any difference? So in that way, if you analyze what would be the chromatic number of a cycle, so you will come to know that idea. So here, find the chromatic number of a cycle is the question. Again, in a cycle, whether it is even cycle or odd cycle, is it the same for even as well as odd, whether the chromatic number is the same for even cycle as well as odd cycle, that we are going to analyze now. So first we consider a cycle CP. What do you mean by cycle CP? It is a cycle with p number of vertices, and to form a cycle we required vertices minimum 3 vertices. So that's why we used to say consider a cycle CP with p number of vertices where p is greater than or equal to 3. Minimum 3 vertices are required to form a cycle. Now label the vertices of a cycle by 1, 2, 3 and so on and so forth, n in sequence. Okay, and assigning one color to odd vertices. So first you consider the vertex 1, and you consider the vertex 3, 5th vertex, 7th vertex, like that. Okay, so in that sequence, if you assign one color to odd vertices and another to even vertices, for the vertex 2, for the vertex 4, for the vertex 6, if you assign another color, what happens? So we consider two different cases. Suppose p equal to 2n, that is, suppose C is a cycle with even number of vertices where n is greater than or equal to 2. Then no adjacent vertices have the same color. Definitely no adjacent vertices have the same color, that is very obvious. So that is the vertices are in terms of even. So therefore you are assigning a first color to, so say for example the second vertex by the color 1. then fourth vertex, sixth vertex, like that. Okay, so in that way, the even vertices, if you color with the same color and the other vertices with the other color, now how many colors we require to color such a cycle with even length or even number of vertices? Then obviously we come to know that the chromatic number of a cycle with the even number of vertices is 2. So even in the previous session we have considered C3, we have considered C4, so C5, like that. For C3 chromatic number is 3, for C4 it was 2, so C5 again it is 3. So if you consider C6, what would be the chromatic number? In this way, if you analyze, you will come to know that the chromatic number of a cycle with even length or even number of vertices, it is 2. Then we will think of a cycle with odd number of vertices. So the case 2 or second case, suppose P is 2n plus 1. So in the form of an odd number 2n plus 1, where n is greater than or equal to 1. Then the first and the pth vertex in a cycle, cycle means it is a closed path. The first vertex and the last vertex, they are adjacent, then only you will form a cycle. So then the first and pth vertex are adjacent, and whenever the vertices are adjacent, you cannot assign same color, so you have to assign different colors. So they are having with different colors or assigned with different colors. Hence it requires the third color for proper coloring, because the first vertex and the last vertex, they are adjacent, so in between, so we require one more color. So this is how a cycle with odd number of vertices requires minimum 3 colors. So that's why the chromatic number of a odd cycle is 3. So by this result, what we come to know, the chromatic number of a cycle is not same. In general, we cannot say it is n or it is k. It depends on whether it is a cycle with odd number of vertices or even number of vertices. If it is a cycle with odd number of vertices, it requires 3 minimum colors, that is the chromatic number of odd cycle is 3, and the chromatic number of an even cycle is 2. So this is how we have discussed the chromatic number of a cycle, considering 2 different cases. Let me consider another example. Find the chromatic number of a complete graph Kp with p greater than or equal to 1 vertices, of course. Okay, a complete graph. In your mind, what do you mean by complete graph? A graph is said to be complete in which every pair of its vertices are adjacent. Okay, in a complete graph, every pair of its vertices are adjacent, then that graph is called a complete graph. So therefore, if you assign one color to a first vertex, any arbitrary vertex, that vertex is adjacent with all other vertices, then how can you assign the same color to the remaining vertices? So therefore, if you think in that way, how many colors we require for a complete graph? Since every pair of vertices are adjacent, even if you consider the first vertex, it is not, you cannot assign that color to the other vertices. It implies if you take any other vertex, that you cannot use for the next vertex, which is adjacent with that vertex, even for the previous one also, because every pair of vertices are adjacent. So very easily, what you can say, the chromatic number of a complete graph is k. Sorry, if it is with p number of vertices, it is p. If it is with k number of vertices, it is k, obviously. So it is left to you how many vertices you are considering. So every pair of vertices in Kp are adjacent. Hence, every 2 adjacent vertices receive 2 different colors. Therefore, the proper coloring of a complete graph with p vertices requires how many colors? P different colors. So therefore, what we can conclude, the chromatic number of a complete graph with p vertices is p. Okay, so this is the second familiar graph. Now we will consider another example. Find the chromatic number of a complement of a complete graph. So complete graph, it implies every pair of its vertices are adjacent. What do you mean by complement of a graph? Complement of a graph means a graph having the same vertex set as that of G, but 2 vertices are adjacent in G bar, the complement of a graph. if and only if they are not adjacent in G. It implies in G every pair of vertices are adjacent in KP. Okay, in a complete graph with P vertices, every pair of its vertices are adjacent. Then if you consider the complement of KP, then no pair of vertices are adjacent. It implies you will get a totally disconnected graph. It implies how many colors we require. Only one color is required because no pair of vertices are adjacent. What is the coloring concept? Adjacent vertices must have different color. But here all vertices are what you can say independent, or you can say isolated vertices. In the graph theoretic way, if I say all vertices are isolated vertices, it implies only one color is required. So therefore the chromatic number of the complement of a complete graph is 1. So what you can say, every pair of vertices in KP are adjacent. It implies no two of its vertices are adjacent in its complement. Then it is a totally disconnected graph. When it is totally disconnected graph, it implies the chromatic number of the complement of a graph is obviously 1 because only one color is required. So therefore, this is the simple example we have considered. Now the fourth example, find the chromatic number of the graph KP minus X. So complete graph with P vertices. What is X? X is one edge, one arbitrary edge. So in a complete graph with P vertices, if you delete one edge, then what would be the chromatic number of that graph? So can you think in that way? Complete graph, the chromatic number is P. In that you are deleting one edge. One edge you are deleting, it implies only those two pair of vertices are with different colors. Okay, only those two, isn't it? If you delete, no. Only those two vertices, if you delete an edge, say E equal to UV. E equal to UV. Earlier U and V are with different colors because in a complete graph every pair of its vertices are adjacent. Now you are considering one edge E equal to UV. If you delete that, it implies U and V are non-adjacent. If U and V are non-adjacent, you can assign the same color which you have used for U to V, isn't it? Okay, if you have used the red color for U, you can use the same red color for V also because there is no edge between U and V. It implies only one color is reduced. Earlier it was with P colors. Now one color is reduced. It implies the chromatic number of a complete graph with P number of vertices minus one edge. If you delete, then it will be P minus 1. So therefore the graph KP minus X is the graph obtained by deleting one edge from KP. Say the edge joining the vertices V1 and VP minus 1. As before, the total number of colors required to color is P minus 1 for these vertices. Okay, to color P minus 1 vertices, we require P minus 1. Then we come to know, or we come to the vertex VP to observe that VP is adjacent to all other vertices except VP minus 1, as I said already. Therefore, the color of VP minus 1 can be given to the vertex VP. So therefore, the minimum number of colors needed to color the complete graph KP minus X is P minus 1. So therefore, the chromatic number of such a graph is P minus 1. Now, we have considered another example. Write the chromatic number of the following graphs. Okay, so one is a tree. You know already what you mean by a tree, where T is a non-trivial tree. A tree is a connected acyclic graph. A tree is a connected acyclic graph. And the second one is complete bipartite graph KMN. One is less than or equal to M is less than or equal to N. And next we are considering another graph G, where G is a unicyclic graph. Means a graph containing one cycle, only one cycle, unicyclic graph. So it implies it is not purely cycle, it may be a cycle also. it is not clearly a cycle. Along with cycle, you may consider some edges or path type attached with a cycle. Okay, so it is not a cycle itself. Unicyclic, only one cycle exists in that graph. Such a graph is called unicyclic graph. Okay, and again in unicyclic graph there are two different cases, whether that cycle is whether even cycle or odd cycle. So one is unicyclic graph with even cycle, another one is a unicyclic graph with odd cycle. Then Wn. So Wn is a wheel. As I said earlier, Wn is a wheel having one vertex at the center and n minus 1 vertices along the circumference. Okay, now what is the chromatic number for these graphs? If I consider a tree, as I said, tree is a non-trivial connected acyclic graph. We are considering a connected acyclic graph, that is a tree. Then what would be its chromatic number? Okay, now the chromatic number of a tree is 2, because when there is no cycle, it implies every pair of vertices. If you consider every pair of vertices, it is adjacent with 1 and it will be proceeded like that. So it implies if you assign one color to one vertex and the vertex which is adjacent with the same vertex, you can color with the other one. But for the next vertex which is adjacent with the other vertex, you can use the previous one. So like that, if you consider a tree, definitely it requires only 2 colors to color. So that's why the chromatic number of a tree is 2. So by observation only you can write the chromatic number of such graphs. The complete bipartite graph KMN, if you observe carefully with different examples, K11, K12, K22, K24, K23, like that, if you think, you may get the result. What is complete bipartite graph? KMN, the vertex set is partitioned into two disjoint subsets, V1 and V2, in such a way that every vertex of V1 is adjacent with each vertex of V2. It implies in V1 set, if you assign one color to any vertex, it is adjacent with all other vertices in the other set. It implies you can use the second color for all other vertices in the second set, isn't it? It implies you can use the same color which you use for the set 1, V1. So you can use one color for all vertices of V1. You can use another color for all vertices of the set V2, because one edge which joins from a vertex of V1 to a vertex of V2. It implies if you analyze in that way, only 2 colors are required. So therefore, the chromatic number of a complete bipartite graph is 2. So like that, if you consider a unicyclic graph, you can use the previous idea. For even cycle we require 2 colors. For odd cycle we require 3 colors. So therefore, that idea is very useful here. But it is not cycle, it is unicyclic graph. So again it will be 2 for a even cycle or unicyclic graph containing an even cycle, 3 for a unicyclic graph containing an odd cycle. And for the wheel, see, for the wheel also again 2 cases, whether the circumference contains how many odd vertices or even vertices. If it contains odd plus one interior, it will be even. If it contains even plus one interior will be odd. So it depends on the number of vertices on the circumference. Okay. Again, a wheel with n, it requires 4 colors if n is even. If it is a wheel with n, where n is odd, it requires 3. See, wheel is nothing but if you remove the center vertex, then it will be a cycle. For even cycle, we require 2 colors. For odd cycle, we require 3 colors. So 2 plus 1 interior, 3 for even. And 3 plus 1 for the interior. So 4 for the odd. So it is very obvious for the wheel with n is even, we require 4 colors. For the wheel n with odd, we require 3 colors. So you can extend the cycle concept in wheel also. So these are the examples, or you can say the familiar graphs we have considered. So we come to know how to find the chromatic number of such familiar graphs. Okay. So these are the reference books. Many times I have told you. So with this we conclude today's session. Thank you.